Hi everyone, this is your second lecture video for section 5.2. In the first lecture video for 5.2, my friend Juan Bernal introduced you to the binomial distribution. Juan Bernal is a math professor over at Mesa College. I went to grad school with him and he was also one of my roommates. He's a pretty cool dude. If you ever go to Mesa College, I would highly recommend that you take math classes with him. Okay, so in this video, we're going to discuss a section 5.2 example, and we're going to make use of the following graphing calculator commands: binom PDF and also binom CDF. I have written down how you access those commands here in these notes, and also what the inputs are. Let's take a look at an example. This is question number 20 from your textbook. In a pediatrician's office, the probability of a no-show for any checkup appointment on any given day is 1 out of 10. Suppose that there are 18 appointments scheduled for one day. Part A, we need to find the probability that fewer than 4 don't show. All right, let's write down the givens for this problem. How many appointments are scheduled for one day? 18. So this is the number of trials. This is a binomial experiment. Why? Because these people, they either show up to their appointment or they don't. So if there are 18 appointments scheduled for the day, that's a fixed number of trials. And these people either show up or they don't. So there's only 2 outcomes. And the occurrence of one does not affect the other. You're not given any information to conclude otherwise. What's a success in this case? A success is the following. So in part A, we're finding the probability that less than 4 people don't show. So the probability of a success is the probability of a no-show. The probability of a no-show is 1 out of 10. So I will write down that P equals 1 over 10. You can also write this as a decimal as 0.1. Part A, find the probability that fewer than 4 don't show. Let me write down what my random variable is for this scenario. Capital X represents the number of no-shows. We want to find the probability that fewer than 4 no-show. So part A is asking us to find the probability that capital X is less than 4. Fewer than 4, this indicates that you have a strict inequality here. Capital X is less than 4. Now let's think about this. Capital X is a binomial random variable. Binomial random variables have to be discrete. The range of possibilities, the range of values for capital X would be the numbers 0 through 18, because you have 18 appointments in total. These appointments represent people. If capital X is less than 4, you can't have a fractional amount of no-shows. You can't have like 3 3/4 amount of no-shows. That makes no sense. So this is a handy trick that you will have to get used to when dealing with discrete random variables. If they can only attain whole number values, if you have capital X is less than some number, this is the same as capital X being less than or equal to the very next number down. So the probability of capital X being less than 4 is the same thing as the probability of capital X being less than or equal to 3. This is a scenario where we will compute this thing using binom CDF. You will use binom CDF when you're computing probability statements of this form here. Let me circle it in red. Capital X being less than or equal to some number. Let me switch on over to my graphing calculator. So I've got to hit the second key and then hit vars. Scroll on down to where, oopsie, go to distribution, scroll on down to where it says binom CDF. We need to enter in our n, the number of trials, which is 18. The value of our probability of a success, 1/10, or the same as 0.1. And what is the x value in our problem? In our problem, it is 3. And then I will hit paste and then hit enter. I'm going to round my answer here to 4 decimal places. So I have 0.9018. As it states here in these notes, you will enter the number of trials, that is n, the probability of a success, lowercase p, and what little x equals to in your problem. Part B, we want to find the probability that at least 2 don't show. So that would be the probability of capital X being greater than or equal to 2. Okay, this is annoying to compute. So your capital X takes on whole number values. If capital X is greater than or equal to 2, that means capital X can be equal to 2, equal to 3, equal to 4, equal to 5, so on, so forth. This event right here is an OR statement, because capital X can equal 2, or 3, or 4, or 5, or 6, etc., all the way up to 18. This is annoying to compute directly. I'm going to use the complement rule. Let me write this in red. The complement of x being greater than or equal to 2 is x less than 2. This probability equals 1 minus the probability of capital X being less than 2. And this follows by using your complement rule from chapter 4. Now, capital X has whole number values. If capital X is less than 2, this is the same thing as 1 minus the probability of capital X being less than or equal to 1. We are only allowed to make that last jump there with the equalities because capital X is a discrete random variable and capital X has to attain whole number values. So computing this probability of capital X being less than or equal to 1, I will use binom CDF again. My n is 18, probability of success is 0.1. My x value in this case is 1. Hit paste, hit enter. So we have 1 minus this result here will kill this problem. Rounding our answer to 4 decimal places, we have 0.5497. Now, please bear in mind why I looked at 1 minus that computation, because what we have here, it says 1 minus the probability of capital X being less than or equal to 1. So to compute that probability of capital X being less than or equal to 1, I used binom CDF, and I subtracted it from 1 to get this result here that was circled. The last one, find the probability that the doctor sees every patient scheduled. Okay, so if the doctor sees every patient scheduled, and capital X represents the number of no-shows, then part C is asking me to find the probability that capital X equals 0. If the doctor sees every patient scheduled, that means that you have no no-shows. So capital X would be 0. Now this is a strict equality here. I need to compute this using binom PDF. Let me scroll up. So when you're computing binomial probability statements of the form capital X equals a number, you will have to use binom PDF. So that's still located in the second same area as I found binom CDF. So you hit second and then vars. Scroll on down to binom PDF. Enter your number of trials, that's n. Enter the probability of success and your X value. Hit enter. Rounding this to 4 decimal places, I have 0.1501. Alrighty, everyone, that wraps up this video. I will see you in the next one.